We know for a regular trivial problem, every eigenvalue has a corresponding linearly independent eigenfunction. So there is only one eigenfunction, linearly independent eigenfunction. And such an eigenfunction is called normalized with respect to the weight function Rx, if this is true. So, okay. So now we can state the generalized Fourier series extension. So let phi n x 1 2 etc. So we let phi sub n be the normalized eigenfunctions of a regular Stirling-Liouville problem on the cross interval a to b. And we let f of x and its derivative f prime of x be piecewise continuous on the cross interval. Okay. Then the series summation n from 1 to infinity Cn phi n x. So the series and is the coefficient seem to be okay. So Cn is obtained by this integral. Okay. So you may think about that this is the square root of r of x, root of x, and the square root of r of x, right? In the L2 space. So we defined L2 space before, and you can think about that. The coefficient C sub n is obtained by the inner product of these two functions. Okay. So this is, can be okay. So you can think about that. Because we in the Stirling-Liouville problem, r of x is assumed positive for all x in the cross interval, right? For our regular problem. Okay, so when we take the square root, there is no questions about to take the square root. All right, and so we call r of x as the weighting function because with weight we multiply with for every function considered, we multiply with the square root of r of x. So we know the Cn here, right? Now, this series will converge, okay, to half of the left limit and the sum of the left limit and right limit of f of x, okay, at each point x in the open interval in B. Okay. So we don't know the convergence behavior of the boundary points. Okay? We just know that the series with coefficient obtained by using this formula will converge to this quantity. Okay, so now we can make a stronger condition on f of x to obtain better result. So we assume that in addition to the hypothesis, okay, to the hypothesis here of theorem 11.5 and 3, the function f of x is continuous on AB. Okay, so in here f of x is assumed to be piecewise continuous. But if we have a stronger condition that f of x is continuous on the curve interval, okay, so we assume continuous. And if k2 is equal to 0 in the first part of equation 11, the two boundary conditions, the first boundary condition at the endpoint x equal to a. So if k2 equal to 0, so that phi n a should be 0, right? Because when k2 is equal to 0, we know the first condition, we know that this is the right? So if this is 0, this implies that k1 ya is 0. But because we know at least one of k1 and k2 not 0, so we know this is non-zero. Right? So this is 0 means that this is non-zero. So this is implies that ya is 0. So any solution of the regular CCLu problem should have this property. So that means that any eigenfunction, right, should be 0 when x equal to a. And when this is equal to a, now, so when x equal to a, this is 0, so this series sum should be 0. Okay? So if this is the case, we assume, then we should assume that f of a equal to 0. Okay? Similarly, if L2 equal to 0 in the second part of the boundary condition at the other endpoint x equal to b, then so that phi and b equal to 0, then we assume that f of b equals 0. Okay? So we have to make further conditions. If k2 equals 0, we have to make that f of a equals 0. If n of 2 equals 0, we have to make another assumption that f of b equals 0. Otherwise, right, no boundary condition need to be prescribed. Okay, for f of x. Right, so this is our assumption. We have three assumptions. Okay. The first one is the general assumption that f of x should be continuous on the closed interval. The second one and third one depends on our boundary condition. This one is for the boundary condition at endpoint A. Right? So if k2 equals 0, then we must have this additional assumption. On the other hand, if L2 equals 0, then we have another additional condition for f of b equals 0. Right? Otherwise, you don't need to put any further boundary conditions on f of x. The conclusion is that then the series in 11.5.7 here, the series here, converge to f of x. Okay? Converge to f of x. Not just the half of the sum of the left limit and the right limit. Okay? It will converge. On what? On the whole closed interval, including the boundary points. Okay? Including the boundary points. And we write f of x equal to the sum of Cn times phi times x. Okay, so this is the strongest result we can have for the generalized Fourier series expansion. Okay, any questions? Okay, now if we change the boundary conditions in 11.5.2 to the following boundary conditions: YA equal to YB, and Y prime A equal to Y prime B. 11.5.8. Okay. Then a Sturm-Liouville equation in 11.5.1 together with the two new boundary conditions in 11.5.8 here. So we have the Sturm-Liouville equation in our first equation in this section, together with this these two new boundary conditions. Okay. This is called a periodic Sturm-Liouville problem. Right? Okay, so when we face with a periodic Sturm-Liouville problem, the vector space of functions we consider will consist of such that 1, U of x is continuously differentiable on AB. So U of x has derivative, and the derivative is continuous. This is so-called continuously differentiable. Okay, and U double prime x, the second derivative exists. Okay, for almost all x in AB. The second derivatives exist. Third one, is in L2. Okay, so the second derivative is dynamic energy. Is L2. Or U of x satisfies the two boundary conditions in 11.8 here. Okay, so to repeat, so P means periodic because the boundary conditions are periodic. Ya is equal to yb, and y prime a equal to y prime b. Okay, so it can be verified that Vp is a vector space. And is a subspace of L2 AB. Okay. Now, in this case, okay, the Sturm-Liouville operator which transform a function in Vp into P U prime minus Pu into another function. And this function of course, so So this is from VP go to level 2. And so this function is in L2. That's the final energy. Okay? So this operator, a linear operator, on the vector space VP is still self-adjoint. And Lu VDX equal to U LV dx. Okay? That means that Lu this inner graph equal to U. For all will be okay. We can have a proof like this one. In the proof, when we prove the property of the self-adjoint property, in the theorem, we prove that the stimuli for this operator is self-adjoint. Okay. For the non-periodic boundary condition in 11.5.2, right? We prove that. So, but we can derive the same thing. We know that actually the difference between these two integrals the difference actually is equal to p of x u prime of x ux minus ux 3 prime of x. Okay, so we know that this one. Right. So now, since U A equal to U B, and okay, maybe I need further condition. Let me write it down. Okay, so this is P, okay, and U prime B. U prime B okay, I need a further condition. Sorry. VB minus UB V prime B. Okay, this one, okay, and minus PA U prime A VA minus UA V plus A. Okay. So this comes to PB. So we need a P. Okay, I need distributive equation with PA equal to PB. I'm sorry. Okay. So we need the PA equal to PB, right? And the two boundary condition by A by B, right? So So you can see that PB is equal to PA and U prime B equal to U prime A, right? Because the periodic condition here, UX satisfies the two boundary conditions. So UA equal to UB, U prime A equal to U prime B. Okay. So the first one is equal to the second one. So the result is that this is equal to 0. Never stop. Okay. So I'm sorry, I forgot to put require PA equal to PB. Okay. So for the periodic stem linear problem, we still have the joint property, and the joint property is the most essential property we need to justify the orthogonality principle as well as the series extension. So any questions about this equation? Okay? Now, okay, so now take an example that consider the periodic Sturm Liouville problem. Y prime plus lambda y equals 0. Y minus pi equal to y pi. Y prime minus pi equal to y pi. Okay. Right. Here we have P of x is equal to 1. Q of x equal to 0. R of x equal to 1. Okay. So you can see that this is implies that p minus 1, p minus pi equal to p pi. Okay, because it's constant. So we just justify that p minus pi equal to p pi. Okay, and these two boundary conditions are periodic boundary conditions. So we know that actually the Sturm-Liouville operator is self-adjoint. Okay, now so again case 1, lambda equal is less than 0. For this case, we know there is no solutions as before. Okay, as before. Case 2, lambda equals 0. When lambda equals 0, the general solution of the Sturm-Liouville equation, okay, this equation, when lambda equals 0, is x. Okay? Now, the two boundary conditions saying that with the two boundary conditions. Okay, so we have C0, C1 minus C1 pi equal to C0 plus C1 pi. Okay, this is from the first one by substitution. And for the derivative, because the derivative of y equal to C1, to C1 equal to C1, of course. It's a constant. So this implies that C1 must be 0. Okay? So when C1 is 0, then C0 is free. C0 is free. Okay? So this implies that. So that there is an eigenfunction y0 equal to 1 over square root of pi. Okay. Corresponding to eigenvalue, not 0 equal to defined degree. So apply 0x is normalized. Okay, this is normalized because that because r of x is 1 here, r of x is 1. Yeah, so the weighting function is 1 means that you don't need to mention the weighting function. So it's 1, right? So this is implies that okay, so we put divided by a constant. So this is normalized. So now 0 is an eigenvalue, and we define 0 as a number 0. Okay. Case 3, lambda equals to mu square. In this case, that a general solution of the Liouville equation. It's A cosine mu x plus B sine mu x. Right. So this is the general solution. Now, with the two boundary conditions, we have A cosine pi mu minus B sine pi mu equal to A cosine pi mu plus B sine pi mu. By applying this equation. Okay. And because cosine is an even function, but sine is an odd function, so we have now to apply the second boundary condition, we have A sine pi mu plus B cosine pi mu equal to minus A sine pi mu plus B cosine pi mu. And the mu has been delayed, okay? Because mu is positive, okay, by all assumption. Okay, the mu has been cancelled. Now, come here, we know we can cancel this one. So this implies that B times sine pi mu equal to 0. Okay, for the first one. For the second one, we know that A sine pi mu equal to 0. Okay, so we have two equations here. Now, if when sine pi mu not equal to 0, we must have A equal to B equal to 0, right? So we have only trivial solution. In fact, we have only trivial solution. Okay. So it's useless. So the only thing is that but when sine pi mu equal to 0, then we obtain, right, two eigenfunctions. Because if this is 0, then A and B can be any constant. So we have 2 degrees of freedom. Okay, and then so cosine and sine function. So we have for eigenfunctions, we have say cosine mu x and sine mu x. Now, when do we have sine pi mu equal to 0? This means that mu must be equal to n. Okay, must be a positive integer. Okay, so that's lambda n equal to n squared, n from 1 to etc. Are eigenvalues. And for each lambda n, they are two linearly independent eigenfunction corresponding to so we set phi 1 x to be cosine nx. And the phi n x will be 1 over square root of pi sine x, which are normalized. Okay. Okay, so we conclude that the trigonometric system 1 cosine x sin x cosine 2x etc. Then is formed by all linearly independent by scaling suddenly pi is formed by also normal eigenfunctions of the periodic Sturm-Liouville problem. Okay? So they are assigned, of course, by the self-adjoint property, and they are normalized here. Okay. Because we put the constant here, so they are also normal. Okay. They are orthogonal to each other, and each function is normalized. Any questions? So from this example, you can see the trigonometric system. Just a simple example, right? A simple example from many different systems. Because this system formed by also normal eigenfunctions of this simple Sturm-Liouville problem. Very simple problem, right? And with periodic boundary conditions. Okay. All right. So let's take a break.